Okay, in this video I want to talk about determining if a vector field on R3 is conservative using what's called the curl, and this will be one example of two, at least two. And first we'll introduce a little bit of notation. What we're going to introduce is what's called the del operator, and the del operator says basically take the partial with respect to x, the partial with respect to y, and the partial with respect to z of something. The curl of f, if we have a vector field f defined as pi plus qj plus rk, the curl of f is given by this definition at the bottom. The way I remember it, I think the easiest way to remember it is what you do is you take the cross product of this del operator with the vector field, and so there's our cross product, and if you calculate the cross product you're going to get this definition at the bottom. The main result here, it says the theorem we're going to use, it says if f is a vector field defined on all of R3 and the component functions have continuous partial derivatives, and the main result says if the curl of f is 0, then f is in fact a conservative vector field. So basically it says we have to compute the curl of the function. If it's 0, it's conservative. Turns out if it's not 0, it's not conservative. Okay, so that's what we're going to do here. Okay, so we're going to take del and cross it with our vector field. So we've got our components I, j, and k. So we're going to take the partial with respect to x, the partial with respect to y, the partial with respect to z, and the components are 2xy. We have x squared plus 2yz, and then we have the component y squared. Okay, so slightly laborious, computation, but nothing too bad here. So, okay, so it says we've got to calculate the partial. Okay, so the part that goes with the I component, so remember how to compute a cross product. I basically just kind of cancel out the I column and the I row in my head, and then we've got a little 2x2 determinant that we have to compute. So it says we take the partial with respect to y of y squared. I think I want to give myself a little more room. And then we subtract away the partial with respect to z of x squared plus 2yz. That's going to be the I component. Remember the the j component changes signs, so we have to put a minus sign on there. So if I cover up the j column and imagine the top row being gone, it says we take the partial with respect to x of y squared minus, then we have to take the partial with respect to z of the term 2xy. So that's going to be our j component. And then we have to add on, so I've ran out of room here a little bit, we have to add on the component that goes with k. And to get that, we'll take the partial with respect to x of x squared plus 2yz minus, then we'll take the partial with respect to y of the 2xy. And that'll be our k component. Alright, so hopefully I wrote everything out correctly here. Let me give myself a little more space just to compute all this at the bottom. Again, if this works out to be simply 0, the 0 vector, it says then we do have in fact a conservative vector field. Okay, so the partial with respect to y of y squared, let me erase that a little bit better real quick. So it says the partial with respect to y of y squared, that's simply 2y, minus if we take the partial with respect to z of the x squared, well that goes away. Then we've got 2yz, and if we take the partial with respect to z, that's just 2y, I. And then if we take the partial with respect to x of y squared, that's simply going to be 0. If we take the partial with respect to z of 2xy, that's also 0. So far so good. And then if we take the partial with respect to x of the x squared plus 2yz, we simply get 2x minus, if we take the partial with respect to y of the 2xy, we simply get 2x, and j, And hey, everything cancels out, and that simply leaves us with 0i plus 0j plus, oops, I wrote j up there, should be a k, plus 0k. And that's the 0 vector, where it says, in fact, hey, our curl of our vector field turned out to be 0, so in fact it is conservative. Okay, so that's pretty much the procedure to show if a vector field on R3 is conservative. Again, if you look at all the partial derivatives, those need to be continuous, but you've got y squareds, x squared plus 2yz's. You have some very nice functions. Notice all of those are continuous. I think in a typical Calc 3 class 2, they're not, I think most people, you should be aware of it, but typically you're going to be given functions that do have continuous partial derivatives. And then it is, again, just a matter of using this curl definition and seeing if you get 0 or not. So here's one example showing that it is conservative. I will have another floating around. I'm sure it'll be one showing that it's not conservative. So as always, feel free to post any comments or questions.